Okay, so today we're going to get into the engine lubrication systems. So we talked about oil yesterday. We talked about the need for lubrication yesterday. We talked about friction and how with friction we generate heat and we generate wear. So we use oil to dissipate heat and reduce wear. So even the best oil is useless if it can't reach the engine's moving parts. So the job of lubrication system is to get oil to the moving parts of the engine. And we'll see we have two different ways of doing this in motors or engines. One is splash lubrication, where we just splash oil around inside the engine, and that's enough to lubricate the components that we're trying to lubricate. We also have pressure lubricated systems where we have to use pressure to go in and lubricate our our friction bearings and get oil to other parts of the engine. Or we can use a combination of those two, where we pressurize oil to the top of the engine and then let some oil splash around and fall back down to the bottom of the engine, lubricating stuff along its way. And that's what we currently use in automobiles. We call them pressure lubricated, but there's plenty of components that are not pressure lubricated in there. An example of a splash lubricated system would be your lawnmower. With very few exceptions, if you have a walk behind or a push mower, it's going to be splash lubricated. Most air compressors are splash lubricated if they have oil in them, with, again, very few exceptions. So you have these technologies. So your lawnmower technology is going to be very different than your engine technology. And a couple of reasons for that. One is the engine has a lot more force in it, higher compression, higher heat. The other is we'd like the engine to last longer in your car than your lawnmower. Lawnmower engines, as a rule, don't last very long, especially when compared to car engines. And you're thinking, wait a minute, my lawnmower is like 10 years old. And you got lucky if it's 10 years old. But you think about it, how often does it run and how long does it run for? How long does it take you to mow a lawn? Is it 20 minutes once a week? And we don't do it 52 weeks a year. So maybe you mow the lawn, half the time, 26 weeks a year, 30 weeks a year. So 30 weeks a year times, call it a half hour a week. That's only 15 hours of runtime a week. Times 10, that's 150 hours of runtime. Compare that with a car. If I am driving an average of 40 miles an hour, which is a reasonable average when you look at city and highway, and I'm going to drive that car for 150 hours at 40 miles to the hour. So what is that? 6,000 miles. Not very long. See what I mean? So how we lubricate things is really important. And how we're getting this oil different places in the engine is also really important. So that's the big difference between a pressure lube system and a splash lube system. Is really the life expectancy of it is one of the things, but also on the other hand, the cost to manufacture. And that's why on a lawnmower or something like that, that's a few $100s, they're not investing that. If you want pressure lubrication in a lawnmower, like on a high-end Toro or something like that, it's a $1,500 walk behind lawnmower because it has that pressure lubricated engine. But what are they designed for? They're designed for landscape contractors to run that lawnmower, 6 hours a day, 8 hours a day for how long? So they need pressure lubrication. So vehicle engines use pressure to force feed lubrication system where oil is forced through the engine under pressure, and we push it through what we call the oil galleys or oil galleries, depends on which book you read it in. And so we're going to take oil out of the oil pan through a pickup into an oil pump, run it through the oil filter, and then we're going to run it up to the oil galleries, and then we're going to pressure feed it into the crankshaft, which has a hollow part that goes over, connects to where the rod bearing would go on. So this all gets oil pressure fed to it. And then oil is fed up to the camshaft. And then if it has variable cam timing, it'll go to the variable cam timing. So my valves and valve springs and my cam lobes all want lubrication. Well, where oil is forced into the bearing, there's no seals on the bearing. So the oil goes into the bearing and is quickly pushed out the sides. And that happens because we want to get that heat that we're generating out of there. So none of these bearing areas, whether it's the crankshaft or connecting rod or cam bearings, are a sealed bearing. So they're open on the side. So they may have 1 to 3 thousandths clearance between the journal and the bearing. And then we force oil into there. And once oil is forced into there and that's suspended, oil is pushed out both sides. And then that oil is circulated back down on the timing chain, back to the oil pan, and then it happens all over again. And as it's circulating, it's getting rid of some of the heat that it picked up being on the bearing surface. So this oil is constantly circulating. So that's why if you're low on oil, it really presents a problem. So say I have a 4-quart engine and I'm a quart low. That means I'm only at 75% capacity. Well, I use oil for cooling. So that means I'm putting a lot more strain on that remaining 75% of oil. And keep in mind that 75% is at different places. I've got a 1/2 quart to a quart in the oil filter. I've got to have some oil in the pan, and then the rest of it is pressurized throughout the system. So as we run low on oil, there's less and less oil in the pan. The pump has to work harder to pull the oil out of the pan because there's not the weight of the oil pushing down to help the pump pull oil in. So you're going to lose potentially pressure and volume as that happens because it's working harder. It's not going to be as efficient. And then it has to pump it through the filter and into the galleries. So, and eventually to the bearing. So if I start running low on oil or have low oil pressure, the camshaft is normally the first part that fails because it's the farthest away. It's the last to get oil. And I've actually seen camshafts stop turning in the cylinder head due to lack of lubrication. And that can happen for a number of reasons. But it's designed so our bottom end, where our pistons and crankshaft are, is the most protected. It gets oil first. On a friction bearing system, the oil is used between what 2 components in order to reduce?
Number 3.
Number 3, the bearing and the shaft. That would be correct. I think someone's been reading ahead here. So we have a couple of different types of oil systems. We use what's called a wet sump system in almost every car produced. There is a dry sump system that's used in racing. Also, it was used on Porsche 911s. It's been used on some other performance vehicles. I'll show you that in a minute. But the most common system, what we normally see on a car, with rare exception, is going to be this wet sump system. So this is where I have an oil pan where I hold the oil. I have a strainer that picks the oil up into the oil pump. The oil pump in turn pushes it into the filter. From the filter, it is pushed over into the bearings for the crankshaft and up to the cylinder head for my camshaft. You can see my oil pressure sender right here. That is what turns the light on the dash. So if there's not enough oil pressure, the light will come on. That's why when you turn the key on, the light comes on. And then when you start the car, the light goes off, because the oil pressure builds and opens the switch inside the sensor with pressure. When there's no pressure, the switch is closed and the light is on because it's controlling the ground circuit to the light. If I start a car, instead of that light going out right away, it takes a while to go out. That's a sign that I have a problem, most likely low on oil, but it's a sign I have a problem. Another issue I might have is when I'm sitting at a stoplight, my oil light will get real dim or start flickering. That means I'm losing oil pressure at idle, but when I rev up, I have enough oil pressure to turn the light off. Again, most common cause is low on oil. If I have either of those situations and I have enough oil in the engine, I would need to remove the sender and install a mechanical test gauge to actually measure the oil pressure in the engine compared to specifications to see, do I just have a bad electrical sender or do I have a more serious problem inside the engine? Things that cause us to have low pressure in the engine if I have the right amount of oil, is either a bad oil pump or I have too much clearance in my bearings. So if I'm only supposed to put oil in there and there's only supposed to be, say, 3/1000 of an inch, and now I have 6/1000 of an inch, I'm going to have less oil pressure because I'm putting more oil into this area. So I'm using more volume. The pressure here is created not just by the pump, but it's created by the restriction that we have in the oil system where it goes to the bearings. So think of it like a water hose. And this is real important for when we get into fuel systems, because return fuel systems work the same way. Think of it as a water hose. If I have water coming out of the hose, I have a lot of water coming out of the hose. But if I put my thumb over the hose, now I put a lot of pressure in the hose. Before, I just have a lot of volume going through it. I don't have that same pressure. That's usually when I find where my dog bit a hole in the hose, is when I put my thumb over it, because that little pinhole that wasn't leaking is now spraying me on the back of the leg. So that's how I find out I get a hole in the hose. But the reason why that happens is, even though I have the ability to create pressure in my pump, or in the case of the house, there's pressure in the water lines, I'm really not pressurizing that hose until I start restricting the end of the hose, which increases the pressure in there. So I need two things. I need what? Pressure from the supply source, in this case, our oil pump. But I also need the restriction of the bearings, that clearance in the bearings, in order to restrict. In other words, everything we pump can't go through those bearings at the same speed that we're pumping it. So therefore, since it's a restriction, we create pressure between the pump and the bearings. And that pressure is what we're reading. So if I have low oil pressure, it's either a bad oil pump or my bearings are flat out worn out. I have a worn out engine, which does happen. What we normally will do is we will test for low oil pressure. If the oil pressure is low, we recommend replacing the oil pump, because the only way I can test the rest of the engine is to put a known good oil pump in there. Some applications, especially domestic applications, older domestic applications, with the V engines and things like that, I can buy what's called a high pressure, high volume pump. They're $5 or $10 more. So if you're working in a shop, normally that's all you install. Because what? I want the best chance of success. I don't want to go back to my customer and go, we have a problem. Plus, even if the engine doesn't have a problem, having that higher pressure and higher volume is only going to help the engine last longer. So it's not going to hurt anything. So traditionally, as a matter of fact, all I've ever installed when available has been a high pressure, high volume pump. We don't put in standard volume pumps because the cost difference is nothing. It used to be like $55 for a regular pump and $60 for the high pressure, high volume. Gee, I can get the upgraded pump for $5 more. It's just a no-brainer. But they do carry both, especially on domestic applications. When I start getting into European or Asian applications, there tends to be just what the manufacturer provides, basically. So even if it's aftermarket, I don't have any choices. It's just a one size fits all. But when I get into domestic vehicles, I tend to have more choices. So here is a dry sump system. The dry sump system has a couple advantages. One is it allows us to put more oil in the engine. So a Porsche 911 6-cylinder would hold between 9.5 and 11.5 quarts of oil, so quite a bit of oil. So you can imagine how big of an oil pan we'd need if I wanted to put that much oil in there. So it allows us to keep it in a separate oil tank off to the side. Also, as we're cornering or handling, that oil's not going to come up and potentially interfere with my crankshaft spinning with the connecting rod having to go through the oil, which it creates drag. Just like if you put your hand through some water, and moving it very quickly, you feel that drag. Or even putting your hand out the window going at 60 miles an hour, you feel that pressure. So it eliminates that. It also gives more consistent oil pressure to the vehicle. So in other words, if I'm doing hard cornering or hard stuff, I don't run the risk of having the sump suck air, which could be catastrophic at high engine speed. So what we're doing here is we collect oil at the bottom. We pull it over with a suction pump, calling it a scavenge pump. We then may go through the oil cooler, depending on temperature. So like the Porsche run an oil thermostat, so it won't run oil through the cooler till the oil is hot. And they do that for temperature control of the engine. And then we have an oil tank. And then we have the pressure pump, which is going to push oil into the oil filter and into the engine. Like, for example, on the Porsches with a dry sump system, you actually check the engine oil with the engine running, which is very unique because we don't ever do that on a wet sump system. Wet sump systems, we always check the oil with the engine off. But a dry sump system, example, the 911, the oil is checked with the engine running. There's a very specific temperature that the oil has to be checked at. So when we used to do these in the shop, we charge an hour labor to change the oil on a 911 because I might be sitting on my rack for 45 minutes just running just for me to get it where I can check the oil. So they could really take up a tremendous amount of time. Therefore, we charge for it. So much more expensive than a regular oil change. So here's an example of an oil pan. So this is called a sub pan right here. So many vehicles today use a sub pan where you have the main pan above it and then a sub pan underneath. And you'll have a drain plug on the sub pan. Here's a full oil pan. So this does not have a sub pan. It's going to go directly to the block. And again, there's our drain plug. We also have some baffling in here to restrict oil movement. This right here is a windage tray. This is an additional tray that was installed on many older domestic vehicles, especially trucks, motorhomes. And this was designed to keep the oil below where the crankshaft is spinning so that the oil doesn't interfere with the crankshaft rotation. Anytime we remove the oil drain plug, we should replace the gasket or seal that's on that oil drain plug. Unfortunately, most quick lubes don't do that. And the consequence of that is that we either strip the threads on the drain plug, strip the threads on the oil pan, or both. So very, very common on aluminum oil pan Hondas. They use an aluminum crush washer on it. When you're not changing the crush washer every time, then you're tightening it more and more to get it to seal because you've already collapsed that crush washer. So now you're trying to collapse it more and more in order to get it to seal. And what happens is you pull the aluminum threads out of the oil pan because you're using a steel drain plug. So you've just created a, to replace that oil pan is about $500, over $500. If you have the special tooling, that pan is repairable on the vehicle, and you're looking probably about $130. All because the customer didn't buy the $1 washer every time they change the oil. And what's the old saying? An ounce of prevention is worth a pound of cure. So splash lubrication, this kind of shows from more of an industrial application. This is not automotive. But it gives you an idea. So here I have, this is what's called a flathead engine. If you notice, my valve is in the block, my camshaft is in the block, and this little piece up here is my cylinder head. So this is very similar to what you see in a lawnmower. And we haven't used this flathead design. Last year was 1965 on a Rambler that we used it on a car as far as the flathead design. And that's why I didn't cover it really in engine design, but the book threw this in here, so I want to at least explain why the valve is where it is and why it's in the block. So this goes around and has a little scooper here, and it's going to just catch the oil as it goes around and splash oil up in here. And the oil just splashes around inside here. So many small engines, whether it's on a lawnmower or a pressure washer or a rototiller or any of those kind of things, tend to be this splash lubricated. Air compressors are splash lubricated. Air compressors last longer than engines do because there's not that force of combustion pushing that piston down. So that's why the bearings last so much longer on a compressor than they do on like a lawnmower. It's because we don't have the force of that combustion. So this is an example of splash lubrication. We're literally just splashing oil around in here and hoping it gets where we want it. There's no filter, there's no oil pump, none of that. In order to have an oil filter on a car, you have to have an oil pump. With no oil pump, no oil filter. So that's another clue. If you're ever looking at things and there's no oil filter, that's a clue. It's probably splash lubricated. So what type of oiling system is used on modern automobiles?
Number 1. Number 3.
Number 3, a combination
Number 3.
pressure and splash lubrication, right? Because we do, like I said, some books are just going to say pressure lubrication, but hold on a minute. We have things that we're just splashing oil on. So not everything is pressure lubricated. So we really do use a combination of the technologies. But every automobile is going to have the oil pump, is going to have oil pressure. So if we look at components of the pressure splash system, combination pressure splash system best meets the needs of modern engine and therefore is in almost universal use. Oil is continuously drawn from the bottom of the engine, pressurized and distributed to engine parts. Oil then drips to the bottom of the oil pan and begins the circuit all over again. So if it's a timing chain engine, we're going to have the ability for oil to drip back over the timing chain going down. There's also oil return holes in the cylinder head that match up to the cylinder block that allows oil to return all the way back to the oil pan. My oil pickup tube or pickup screen is mounted on the bottom of the engine. This is connected either directly or indirectly to the oil pump. This has a screen in it that's about the consistency of the screen on your window, except for it's made out of metal, but the squares are about that size. So this is only designed to stop large things from going in the oil pump. This doesn't keep the oil clean. It just prevents large things from going in the oil pump that could damage the oil pump. So if I'm working on an engine and I allow debris to get into the engine, or pieces of silicone to get into the engine, or pieces of gasket to get in the engine, those are the things that this screen will catch. The issue is as it catches it, it plugs up. If it plugs up too much, eventually you starve the engine for oil, especially at highway speed. The other thing that can cause it to plug up is lack of maintenance. So if you have a lot of sludge buildup in the engine, the car hasn't been changed, that sludge is going to break off into hard pieces of carbon, and those hard pieces of carbon get sucked into the oil pump screen and lodge there and restrict the oil pump screen. And we had a vehicle in the school a couple years ago. It was a faculty member's car, and they brought it in because it didn't run on all the cylinders. So we got it running on all the cylinders for them. Went for a test drive. Oil light came on, came back. We tested it, found that it had no oil pressure when you rev the engine up, but it had oil pressure at idle. Typical plug screen. We pulled the oil pan off. Screen was completely plugged up. We cleaned that, put new oil in it, put it all back together, went on a test drive around the block, and it made it just back into the service bay before the engine locked up and it needed an engine. So they had already done the damage to it. It's funny that they mentioned that their car wasn't running on all the cylinders, but didn't mention the red light that comes on every time you accelerate. So customer had to pay for the parts that we put in. It was a faculty member. So they paid, hundreds of dollars in parts for a car that had to go to the junkyard. And it was really all due to lack of maintenance. And also that's really important that you're honest with the technicians working on your car. Don't hide things about lights coming on, because we would have addressed the problem differently had we known that. So it's unfortunate, but things happen. So the oil pump, we have a couple different type of oil pumps we use. One is a rotor style oil pump. The inner rotor drives the outer one, and the oil is forced out the pump outlet. Higher atmospheric pressure outside forces oil into the pump as it fills the spaces between the rotor lobes. Now, from here through fuel, actually even into some other things, the book is really interesting how they talk about this, because it's really confusing. We use vacuum to pull oil into the oil pump. Vacuum is anything less than atmospheric pressure. What they're saying is the pressure in the atmosphere is pushing the oil into the oil pump. Well, that's true, but only because we created less pressure between the oil pump and the oil, allowing the higher pressure to move the oil. So instead of saying the oil pump pulls the oil in like they did in books when I was younger, this book really talks about, well, the higher atmospheric pressure is pushing the oil. And to me, I think that's a confusing way of explaining it. It'd be like if I am drinking out of a cup with a straw. I think most people would say that by creating a vacuum or creating suction with my mouth, I'm pulling the liquid up the straw into my mouth. What the book is saying is that it's the pressure in the atmosphere on the liquid in the cup that's pushing it up the straw and into your mouth. Both of which are technically true, but they're true only because I made that low pressure area. And so I think it's really confusing how the book does this, and the book does this with fuel also. And that's why I point that out, because I have people that read that and they go, huh? In my mind, because I'm not terribly bright, I think it's easier to think of that I'm pulling stuff up the straw than things are pushing stuff into the straw. Even though both do have an effect on the efficiency. And that's why I mentioned when you're low on oil, we have less weight pushing down, causing the pump to have to work harder to pull the same amount of oil in. Same thing would be true with your fuel pump. And yes, it's the atmospheric pressure on the liquid, but it's also the weight of the liquid above the wherever the pickup point is. That's why if you're pulling liquid out of a cup or a milkshake, right? So let's take a milkshake. When you first start sucking the liquid out of the milkshake, it's pretty easy. As you get down to that last quarter, you're working harder to get the same amount of liquid up the straw. And that's because you don't have the help of that weight of the liquid pushing down, making it easier for you to suck the milkshake out of the straw. You have the same pressure in the atmosphere pushing on it. You're creating the same amount of vacuum, but you've changed the weight of the liquid in the cup. That means you're working harder the closer to the bottom of the cup you get. And that's with a milkshake, a soda, anything you're drinking through a straw. So pumps work the same way. And pumps are going to work harder when there's less volume. And that's why fluid levels become important. We're going to get into that with fuel also and fuel levels. But I wanted to point that out because they really get in this whole pressure thing and atmospheric pressure and pressure differences. And it's not that simple, first of all. And second of all, it's confusing how they say it. So a geared pump, very popular style of pump. Meshes the gear meshes with the second gear, and the oil is forced from the outlet into the oil gallery and toward the oil filter. And again, it gets into higher atmospheric pressure outside, forces oil up into the inlet, which fills the space between the gears. Let me tell you, if you don't spin it around and you shut your car off, there's no oil here. Right? So it's not atmospheric pressure alone that's putting oil in the pump. The pump has to rotate, create a low pressure area, vacuum, which pulls the oil in. And it's the vacuum is anything less than atmospheric pressure. So it's that pressure differential that allows it to work. So the first two types of pumps we normally see mounted underneath the crankshaft or in the oil pan area. Our third kind of pump, the crescent pump, where we have an inner gear driven by the crankshaft directly and an internal tooth gear meshes with the outer one. And oil is carried between the gears in the crescent before being discharged to the outlet port. These are mounted on the timing cover. So this is mounted directly on the crankshaft. So the crankshaft will be right here in the center. It's going to mount directly on the crankshaft, where this design and the previous design are either driven by a shaft or driven by a chain or driven by a gear, but they're not directly mounted to an oil pump. And they may not even be directly mounted or mounted remotely to a crankshaft. For example, a lot of the oil pumps on the first design here, this is a very common design used by domestic manufacturers, and it was driven by an oil pump shaft that was connected to the bottom of the distributor, run off the camshaft. This next design here, very common design we see today, and this design is not exclusively, but commonly run by a separate chain connecting it to the crankshaft, and it has an oil pump cartridge that mounts underneath the crankshaft for a lot of volume. And then this is definitely a favorite of Asian manufacturers, but not exclusive to Asian manufacturers. And this is mounted right on the front of the crankshaft on the timing cover. So if I have to replace an oil pump, it's really important to figure out, do I need to take the oil pan off, or am I taking the belts off and the harmonic balancer off and it's right there? So that's why it's important to always go to the manual if you're not familiar with the vehicle, even though you can look up the labor time in a different place, but you want to go to the manual. What's involved with taking this apart? Do I need to take the oil pan off? Do I need to take belts off? What do I need to do to access this? Because if you're preparing an estimate, you need to include parts and labor required to do the job. Plus, you'd hate to put the car up in the air and take off the oil pan only to find the oil pump's not there and you took it off for no reason. So it's always important to double check the component location and the procedure when repairing things on the mobile, because there is so many variations and you never want to assume that, oh, it's this way. It's always worth taking the extra couple of minutes and looking it up. Which oil pump design is mounted on the front of the crankshaft?
Number 4.
Correct.
Hey,
So pump drives, most engine oil pump drives, oil pumps are driven one of two ways: a drive rod from the camshaft or directly by the engine crankshaft via chain or mounted. Many newer engines use the pump installed in the front cover, driven by the crankshaft. So I want oil pressure, but I don't want too much oil pressure, because if I have too much oil pressure, I can blow my oil filter apart. I can create oil leaks that I wouldn't otherwise have. So we have to have a way of controlling oil pressure. So I mentioned part of that control is the restriction at the end of the oil, so the clearance on my bearings and so on. Part of that control is how fast the engine's going. So it's a mechanical pump, so it's going to make less oil volume at idle than it does at 3,000 or 4,000 RPM. So, my output is somewhat controlled by that. We have some vehicles that I don't have in this PowerPoint presentation, but we're seeing on some 2019 vehicles now, 2018 vehicles, we're actually using the computer to help control oil pressure, to keep oil pressure low. And they're using a couple of different ways of doing that. So we have some computerized ways. The book here is showing what all vehicles have, which is an oil pressure relief valve. So all vehicles are going to have this oil pressure relief valve. And so here, the oil pressure is affected by the size of the leaks in the system. That's what I was mentioning, right? How worn is my engine? So if I have a small amount of leakage, I would have more pressure. As I have a worn engine, I would have less pressure. If my oil is thick, I'd have more pressure. If it's thin, I'd have less pressure. So again, viscosity of the oil is going to affect that. And that's why a lot of times we see on engines that are worn, I might have okay pressure when it's cold and then very low pressure when it's hot. So that does affect it. It also comes down to the volume of things. So then when I look over here, oil pressure is affected by change in the volume flowing through it. So depending on how much volume I'm flowing, also I can change my pressure. So it's normal to have higher oil pressure at 3,000 RPM than I do at idle, because the pump's spinning faster. I have more volume, even if I have the same size restriction. So if an oil pressure exceeds what is allowed, we have a relief valve. And the relief valve is just a spring-loaded mechanical valve that is going to allow oil to return back to the oil pan once it exceeds the pressure of the spring in the valve. So if you're doing race applications, you can actually modify these. You can play with these with washers. They make some different pressure relief valves for oil applications to kind of boost your pressure. So, I mean, just like anything on a car, there's stuff out there you can play with it with. Be careful, you get too much pressure, you literally will blow an oil filter apart. Honda many years ago had an issue with the oil pressure relief valve sticking, and we would get cars towed in where they had blown the oil filter off of the engine or blown the oil filter apart, where the bottom part and where the crimp is, it popped apart and it just came apart in pieces, or just popped to let all the oil out. So, not a uncommon thing. at that time. So I've seen it several times over the years. Like I said, those Hondas have all long gone to the junkyard at this point. But that was a real common thing we were seeing in the late 80s with Honda. So it does happen. So if you see an oil filter that's popped off, better check oil pressure, better look, and not just check it at idle, but check it at high RPM or check it going down the road. And that requires a mechanical gauge, because odds are the reason why the filter failed is excessive oil pressure. So oil filters, two basic types of filters. We have a full flow filter and a bypass filter, and I have a couple better pictures of that. But it has to do with how we're flowing the oil through the filter. We see pleated paper is probably the single most common filtering medium, although they do use other materials like fleece for some high mileage filters, and also different types of cellulose, which paper is basically cellulose, but instead of being pleated, it might be fully stacked, like I'll show you on a deep filter. Filters tend to filter to about 20 micron is pretty standard. So what we're looking at here is surface area. The more surface area you have, the more filtration you have. So on a cheap filter, maybe I have 60 pleats going around, and then the next expensive filter has 100 pleats, and then the really good one has 150 pleats. I mean, that's one way where you'll see the difference in filter pricing when you open them up. You may have very little filtration. Yeah, you got paper there. Yeah, the metal's the same size, but the amount of pleats, the amount of surface area for filtering is significantly less. So that is something that we look at. This happens to be a cartridge style filter. So we have two different types of filter that we use on cars today. One is a spin-on filter. The other is a cartridge filter. So in the old days, like we see this old example down here, and that's real old. I'm surprised they didn't do something a little newer for the book. Is a cartridge filter. So in the old days, everything was a cartridge. Then around the 1960s, there's this new thing that came out, which was a spin-on filter. And these were awesome because these old cartridges would tweak, leak, not seal up correctly. I mean, I've had some of these old metal ones. If someone bends them, you'll never get them to seal. And that's oil pressure, right? That's right from the pump. So if it's not leaking right, so if it doesn't leak right, someone could lose all their oil very quickly. The engine could blow up. So you always really check these afterwards, made sure they were dry. There are some better versions that the Europeans used that were made out of aluminum. I've still seen issues with them, but they were a much better system. But then these spin-on filters came out. So this had a square cut O-ring that fits in the groove at the base of the filter and seals the filter to the engine block or oil filter adapter. So these really took over the market. So almost everything used this spin-on filter. And then in the late 90s, we saw Europe say, we don't want spin-on filters anymore because of the waste. So Europe now only allows cartridge paper filters or cartridge filters. There are some fleece ones also. So we see a lot of manufacturers now, Toyota for one, that have moved away from a spin-on filter and gone to cartridge filters here in the US. So we now see probably a pretty good mix between cartridge filters and spin-on filters on cars on the road today in the US. So it's really changed a lot. For a long time, it was only Europeans had the cartridge filters, and then Europeans finally went to spin-on, and they did that for a few years, less than a decade. And then mandates from Europe came back to cartridges. So we see a lot of cartridges on European vehicles because they don't want the waste of the whole oil filter. Now in the US, in many parts of the country, we recycle these, and the number one thing they make out of old oil filters is rebar. So they do get recycled. Matter of fact, these are all hazardous waste. I'm not allowed to throw them in the trash anymore. They have to be collected, and then they have to be hauled off by a approved hauler. And I have to get paperwork from them, and it's all tracked, and I have to have that available. And that's true at the school. That's true if I have a shop. So when I started in this business, they all went in the trash can. That's where everything went. Over the course of the last almost 40 years, things have changed a lot. So a lot of stuff that we used to throw in the trash, you can't throw in the trash anymore. It has to be sent here or sent there or recycled in a certain way. So here is filter operation. And what I want to point out is, see how the oil comes in the outside, goes through the material, and then out the inside. So one of the mistakes people make is a lot of these spin-on filters come wrapped in plastic. And you can see the hole where it screws on, and people take their finger and they put it in the hole to break the plastic and then pull the plastic out. And there's been cases where a small piece of plastic stays inside the filter. Depending on engine design, it can be anywhere from a problem to a catastrophic problem. In the case of the Honda 1.5s, when that's happened, and I have some neat pictures of it, it actually seizes the camshaft in the cylinder head and the camshaft breaks in two. It's pretty exciting, and destroys the entire top of the engine because that little piece of plastic plugs the oil gallery going from the cylinder block to the cylinder head, plugs it up completely, no oil in the cylinder head stops turning, the pistons keep moving, so the pistons hit the valves, and the whole top of the engine's bad. Potentially the whole engine's bad, depending on the severity of the hit. And they were seeing this on engines with as little as 5,000 miles. So imagine your brand new Honda, you take it in for the oil change at 5,000 miles, you drive home, and within a day or two, your engine stops working. Catastrophic failure. So that's something that's something we shouldn't do. It's human nature to want to do it. I see a lot of people do it, but it can have very dire consequences, because anything that's in this part of the filter is going to go right into your oiling system, no protection, and it may completely destroy the engine. So this is a regular filter. We also see we have a relief valve. At the back, the relief valve is for pressure. So if this becomes too plugged, then an oil can't flow through it, or it becomes too restricted, the relief valve will open and allow oil to go through here unfiltered. So we were talking yesterday about, hey, how about leaving the filter on? How about, these other things? Well, the filter itself is not going to cause a failure, and you're not going to know how well it's working. Just like you don't really know how good your filter is unless you've seen a cutaway of it or done some research. But there comes a point where if the filter stops working, now you're just driving a car with no oil filter. And we stopped doing that in the 50s and early 60s. And even then, we only changed the oil every 1,000 miles. So really not a good idea. This is a depth style filtration oil filter. And if you look here, the media is much different. It's not a pleated paper. So we have a lot more surface area. And this works more like a sand filter would. So when we filter water with sand, we pour water in the top, the water comes out the bottom very clean, because the water's had to find all these little nooks and crannies through this sand, and any particles are filtered out in the process. So it's the same principles here, although this is not sand, but the same principles here. Oil is going to go through here, and it doesn't have one direct path or a short path like it did going through that pleated paper. Here, it has to go through this whole depth before it gets to here. So this was very common on European engines. A lot of European manufacturers use the depth type filtration oil filter. And that's why some of these filters are so expensive and weigh so much. I mean, you can feel the weight. And sometimes what you'll have is, the man filter or one of the other OE manufacturers of filters for European vehicles, their filter is pretty expensive. Well, hey, we got this white box XYZ filter that'll work in your car, and it's a third the price. Do yourself a favor, feel the weight of them. The expensive filter probably weighs a lot more. Why? Because it's a depth style filter as opposed to just pleated paper. Well, why do you think the manufacturers, because they're buying all these filters, right? They bought a few million of them for all the cars they've sold. Why do you think they're spending extra money on this? Because that's what the engineers decided they wanted for their engine to last a long time. So that's one of the big cost differences that you see when you see that, a major brand filter, a Miley or a Man, and I'm blanking on the third name, that we see for European vehicles, they may be a lot more expensive than an XYZ Auto Parts oil filter for the same car. Different filter technology inside. And one quick way is just feel how much it weighs. Some of these filters for some of these European vehicles are extremely heavy. So our oil galleries and lines, the main oil gallery runs lengthwise in the block and connected to most other galleries. Passages from the main gallery are drilled into the main bearings. Crankshaft is drilled to carry oil from the main journals to the rod journals. So this is just what I talked about earlier today, and how we're getting oil from the oil pump through the oil filter to the galleries, and then pressure feeding it into the crankshaft, which has hollow passages that feeds it over to the connecting rods. Some engines use separate lines to carry part of the oil flow. So some engines will use external oil lines. Toyota did this on the 3.5 liter. So we will see external pressurized oil lines on some engines. Mazda does that on the Miata. So it's not uncommon. Some rods are drilled through the full length to carry oil to the wrist pin. So I may be pushing oil up the connecting rod all the way to the wrist pin. Others have tiny holes that line up with the crank journal once every revolution, which allows pressurized oil to spit on the cylinder wall. So we have different ways of getting oil to the places we want it. So here is another diagram of an oil system. In this case, we have the picture where we're coming up from the pump, from the strainer to the pump, to the oil filter, to the oil cooler, now into our crankshaft, up to our cams, and eventually to our scissor gear mechanism or our variable camshaft. So here is an oil flow right here. Here's our oil pan. We have the strainer, the oil pump. If I have too much pressure, the relief valve puts it back to the oil pan. I have the oil filter. I have a bypass valve here, oil cooler, then the main oil hole, our main gallery. From there, I'm going to go to the crankshaft, connecting rods and pistons. After each of these, you notice it returns back to the oil pan. So I have the ability to send oil back at each of these places because none of these are completely sealed. From here, we're going to send oil into the cylinder head. I have the left head and the right head, so two different places. We got the camshaft journals, camshafts, valves, and lifters and stems, and then my scissor mechanism. And if you notice, as we go up, each of these components is returning oil back to the oil pan. So, and they should have put the camshaft journals here going back, but cams and camshaft journals, I'm not even sure why they broke them out separately in the description. But you get the idea. We're sending oil back at every point of the way. This is not a sealed system. It's not like we're pressurizing a sealed hose. We are constantly flowing oil through this because we want to get rid of the heat. And we want to keep everything lubricated with fresh lubricant. So according to the chart on the previous slide, which component is the last to receive oil pressure?
Number 4.
Number 4. Think about it. We start at the bottom, work our way to the top. What's the last thing at the top? In this case, of the choices, the valve lifters. That's why if you run low on oil, the lifters start ticking. They start making noise. So when I have a car with the oil light on and I start it up, one of the things I listen for is, are the lifters or are the valves making noise? What does the engine sound like? The engine sounds nice and quiet. Odds are I have oil pressure, but it's just a sending unit problem. If I have an engine that's making noise, either I have an engine, most likely have an oil pressure problem, either no oil or a bad oil pump or a worn out engine. So here's another picture kind of showing the same thing. Again, it's kind of hard to get this via, online. So I tried to put some different pictures in here that I found. So here we're pulling oil up, going to the oil pump. From the oil pump, it's going to go to the galley. It's going to feed the crankshaft. It's going to come up and feed, in this case, our auxiliary shaft and our camshafts. You see the oil filter here. So oil enters the bearing. Bearing receives oil from the hole drilled through the bearing support. The insert has a hole that aligns with one in the bearing support. So there's a hole in the bearing support to allow this oil to get to the bearing surface. Oil passes through and engages the turning journal, and oil is pulled between the insert and the journal. Oil is constantly forced through the bearing. So if I look here, here's a connecting rod bearing. This one has a little squirt hole in it that they're showing. They don't all have that. But I have the machine surface here. We set the bearing in the machine surface, and we have holes that are going to line up. In this case, they're showing the hole here. You can see where there's room for oil to move in the bearing. So this is the bearing right here. This is the journal. So you have the bearing surface, the hole goes through everything. And you can also see where you have a low spot, which allows oil to go around the bearing and be forced out on both sides of the bearing. Squirt hose holes in oil galleys. Heavy duty engines have oil nozzles to spray oil onto the bottom side of the piston. This is really a diesel only thing. Oil is fed in the cylinder head through the oil galleries and onto the camshaft bearing and valve train. Oil drains back to the sump through the drain back holes connected to the cylinder head and engine block, as we discussed. So retaining oil in the engine, gaskets used throughout the engine, sealants, room temperature, vulcanizing, and anaerobic sealants, depending on application. The main difference between the two, actually there's several differences, but really the main chemical difference between the two. In order for RTV to seal, to set, it has to be exposed to air. Anaerobic sealant will only set up in an absence of air. So we use anaerobic sealants where I have like two halves of an engine or two halves of a transmission that are machine surfaces going together, very precise fits. Where I have a nice wide surface, I'm bolting them together. I'm going to use an anaerobic sealant there because a silicone will never cure in the center of that because there's no air getting to it. Room temperature vulcanizing sealants are broken into a couple different areas, depending on what I want to do with them, as well as they have some specialty sealants. The big thing with room temperature vulcanizing sealants is that some will damage catalytic converters. So I'll always want to make sure I use a premium automotive sealant, and which is very different than the silicones we use elsewhere. We use oil seals. Really, the definition of a seal is something that is keeping a liquid in around a rotating shaft. So if I have a shaft that rotates either continuously or just back and forth like a manual valve on a transmission, I use a seal because a seal is going to connect something that doesn't move to something that does move, rotates, and we're going to need a seal for that. If I have two pieces and they don't move, that's a gasket. So RTV or sealants are a type of gasket. They're only designed for two stationary objects. As soon as I have one thing move and the other part is stationary, then I need to use a seal. So many times manufacturers will use sealants from the factory in place of a gasket. Sometimes when I'm servicing something, I have a choice of using a gasket or a sealant. Other times I don't. It depends on how machined the surfaces are, the tolerances, and so on. So we always want to follow manufacturer's recommendations on that. So here's an oil pan gasket. These can be made out of cork, they can be made out of paper, felt. Also, they can be made out of metal with silicone over the top of them, where it's actually a hard silicone, not super hard, but it's not liquid silicone like you get out of a tube. So we have some different options. Our seals, our rear seal by the flywheel is called the rear main seal on the crankshaft. The front is just called the front seal. So on my crankshaft here, I can see the front seal and I can see the rear main seal. So if someone says their rear main is leaking, this is what they're talking about. Rear main seals come in two different ways. They can either come as a one-piece seal, where it would be installed by removing the flywheel. They also come as a two-piece seal, where you have to remove the oil pan, you actually remove the rear bearing journal, and you replace the seal. That way it comes in two halves and you put them together. That's not our choice. That's a choice the engineers made. We just have to live with it, but it's important to know what kind of seal you're putting in before you start taking the car apart. Do I need to take the oil pan off, or do I need to take the transmission out? And sometimes it's not that easy to find out. Sometimes you're ordering the part to see what the part looks like before you bid the job to the customer, because nothing is really telling you. Or you don't trust the directions because you've been burned before. And one thing that AllData, Mitchell, they all do, and even manufacturers do, is they cut and paste last year's instructions into this year's instructions. So if you're at a transition year, it's very possible that you could follow the instructions and still be wrong, because they just cut and pasted the instructions from last year to this year, and they didn't change them, or they didn't realize that the engine design had changed. And that happens sometimes. I've been victim of that, where I've pulled an oil pan off and, ooh, this is a one-piece seal. This is wrong. Or I pulled a transmission off because it's supposed to be a one-piece seal and it's not. Or in some cases, someone did an engine change. So they didn't put a completely different engine in. They put the same size engine in, the same manufacturer engine in, but a different year of engine. So you're following the instructions for the year of the vehicle, only to find out that the rebuilt engine someone put in was of a slightly different generation. Here's an example of an oil slinger. And we can see here we have the crankshaft. We have the oil line coming in to pressurize the rear bearing, the main bearing. And we have an oil slinger to catch some of this oil and flow it back to the oil pan. And then we have a seal right here. So some cars don't have this slinger, although a lot do. MG, old MGs, didn't even have this seal. They relied completely on the slinger to get the oil back. So they always dripped a little bit, but you're never going to get them to seal. Now there's a company that actually has a retrofit kit where you can go in and install a seal on them, because as the cars have become more and more collectible and more expensive, people don't want oil dripping. So now, oh, we got to fix that, even though they dripped from the factory. Or oil pressure and level indicators, oil pressure and level, instrument panel mounted, oil pressure gauge, oil pressure warning light. So do I have a gauge? The gauge is not going to be overly accurate. The real purpose of that is just to let you know you have a problem or you're okay. So don't get too obsessed with the numbers. Electric oil pressure gauge uses a different sensor unit than used by the electric water temperature gauge. Of course it does, because we're not measuring water temperature. However, if it is a normal electric gauge and is not going through a computer, the electrical circuit is going to be identical to my coolant temperature gauge. It's going to be identical to my fuel level gauge. I have a variable resistor for a sensor, and I have a fixed resistor in the gauge. And as the fixed resistor in the gauge heats up due to more current flow, we read higher on the gauge. So the electrical circuit, series circuit, two loads, one fixed, one variable. So that's going to be true for a regular electric gauge, no computer. But that's also true if I have a computer. We learned about our ECT sensor, where I have a variable resistor and a fixed resistor in series. Based on what the variable resistor does, the voltage between the variable resistor and the fixed resistor changes. Same thing we're doing with a gauge here. So if I have my pressure gauge connected to an instrument cluster or connected to an engine computer, PCM, I already know how the circuit works. I have a variable resistor in the sending unit. There's a fixed resistor in the computer, and it's sending out a fixed voltage. And based on the voltage drop between the two resistors, that tells the computer what the gauge should read. So how would I test it? Well, easiest way is unplug it. I should be cold, low, plug it in. I'm going to be what? High pressure. In other words, does the gauge read low when it's disconnected? And if I jump her to ground, does it read high? And that's pretty universal, regardless of what car you're working on, regardless of what year of car you're working on. So again, the circuit that we learned when we looked at sensors, it's the same circuit. Is it a switch? That's easy. Open, close. If I touch ground, the light's on. If I take ground away, lights off. It's an easy switch circuit. If it's a gauge, I got to have two resistors for it to work. Either one's in the gauge on an older car or one's in the computer on a newer car. So again, when we learned about switches, we learned about thermistors, we learned about sensor circuits. All those apply here. Again, we only have a couple ways of building something in reality. We just keep calling it new things or doing new things with it. So when we break down to going back to it's something you already know, I don't need to spend 5 slides explaining it again because we've already gone into that. It's the same exact system. And some of these I have more pictures for than others as we go through cooling system and some of these other things. Some vehicles use a warning light to indicate when pressure drops below a certain point. Most warning lights don't turn on until somewhere between about a half a PSI to 1.5 PSI. So by the time that warning light comes on, you have a problem or you got a bad setting unit, which means you still have a problem because you don't know the engine. So if that red light's on, you really want to tow the vehicle. People ask me all the time, can I drive it? My short answer is it's cheaper to tow it. So even if you're spending $70 on a tow, it's still cheaper than $7,000 for an engine. It's cheaper to tow it. And what's the worst that happened? It only needed a setting unit. You could have gotten away with it. You're out $70. That's cheap insurance versus an engine. So here is a couple of them. Here's an active warning light. This warning light will come on every time you turn your key to the run position before you start the car. You start the car, that light will go off. Here we have a gauge. The gauge is reading 0 and the computer's coming up and telling you, hey, check oil pressure. The gauge is reading 0 and there's usually a corresponding buzzer or dinger that's going to go with that to get your attention. Since gauges do not get the same attention of the driver as the red light does, normally there's some audible thing that'll go with that on many vehicles, either a dinging sound, something comes up, says check gauges, in this case, very specific, check oil pressure, but they're doing things to get your attention because they know customers who really don't look at gauges that well, or when a red light pops on the dash, that gets your attention. Or in this case, a yellow light. So here's our oil pressure circuits that I was just talking about. So we have a light on this side and a gauge on this side. So if I look here, this is a simple switch circuit. I have power that comes through to the light and then ground is connected in the switch. So if I have pressure, the light will be off. If I don't have pressure, the light's on. So no pressure, it's connected. As we apply pressure, we push it off. It no longer makes the electrical connection. Light goes off. It's a simple switch circuit. Series circuit, here's our load. All this is a switch. Here we have 2 resistors. I have a resistor inside the setting unit. I have a resistor inside the gauge. So I have power comes through the gauge, through the setting unit to ground. As we change resistance in the setting unit, we change the amount of current flow through the gauge. The more current flow through the gauge, the internal resistor heats up, bending the needle towards high. So we can see here low pressure and high pressure, and they kind of show you a little bit of what's going on inside here. Whether you see the deflection here versus the deflection here. We're changing the current flow going through the sensor, which affects the voltage drop between the 2 resistors and causes this resistor to heat up. If this went to a computer or a module, very similar, except for instead of a gauge, we just have a resistor inside the module, just like we did for our ECT and IAT sensor signals, where we use the thermistor, an internal fixed resistor and external variable resistor. Cooling of the oil. This is critical because if oil gets too hot, it'll carbonize or coke. Excessive heat causing oil to form solid lumps that clog the pickup screen, fill up the oil control rings on the piston, and create other damage. Oil is cooled by the airstream passing over the thin oil pan, thus drawing heat out of the oil. Some oil pans that are made out of aluminum have cooling fins cast into them to provide more surface area to dissipate that heat. Keep in mind, if I have a 4-quart engine and I'm 1 quart low on oil, I've lost 25% of my cooling capacity through the oil, which means I'm going to what? Carbonize the oil, coke it up. That's why running cars low on oil is so catastrophic. And some of the cars that hold 6, 7 quarts, you don't have low oil pressure till you're down to a quart of oil. Well, how much coking has happened and carbonizing has happened as we're going down, and we're running a small fraction of the oil that we should in that engine. And that'll break down even the best of oils. So auxiliary oil coolers, there's 2 different types of oil coolers we use today. One, which is very popular, mounts on the base just below the oil filter. And so it mounts just below the oil filter, and it has coolant that cycles through it, and oil goes through the center of it. And it allows us both inside and outside, because we're of course feeding to the outside of the filter and returning through the inside, and allows some cooling. And manufacturers like this, it doesn't take up a lot of space. When we're manufacturing a vehicle, I don't have to run all these extra hoses or other lines to an external cooler. So as I'm assembling a vehicle, I'm able to just drop this as an assembly. The downside of these is that they do fail. They will cause oil and coolant to mix, so they can mimic a blown head gasket. If I think that is the case, what we want to do is disconnect the hoses from the cooler and just loop the hoses back together, clean everything up, and see, does it come back? We can try pressurizing the cooling system to see if we get some coolant coming out, which does happen. Normally what this will do is it'll put coolant in the oil, not oil in the coolant, although it can go both ways, and I've seen it go both ways. But when I shut the engine off, my cooling system still will have about 15 or 16 PSI, where there's no pressure in my oil system. So, and it takes a long time for that pressure to dissipate. So it wants to push coolant in the oil. So if my oil looks like a chocolate milkshake and I have one of these oil coolers on my car, I would suspect that the oil cooler is bad versus having a blown head gasket, which is what that color of the oil would normally indicate. So in order to be sure, I got to change the oil, clean everything out, bypass the cooler, drive it. If it doesn't turn into a milkshake again, then I know I have a bad cooler. These coolers are several $100s normally. So it's not something I just want to throw on because I think it might be it to see what happens. It is something I'm going to want to bypass and check normally. I can also try pulling it off, pressure testing it on the bench. I mean, I do have other options depending on how much time I have to see if it's failed. But these are a common failure item. Also, what will happen is the O-ring right here that goes between the cooler and the block will leak on some applications. Nissan has a real problem with this, and they have an updated seal they use that's a different color. I don't remember. I think the original ones were orange and the new ones are green, but they changed the color to let you know it's the new seal. Another type of oil cooler we have is a cooler that would mount in front of the radiator. So here I would use pressure to push oil from the engine through hoses and lines up to this cooler, and then I would exchange this heat in the oil with the air. So this is also a common type of oil cooler. This would be mounted in front of the radiator. Some manufacturers have also built the oil cooler into the radiator, very similar like we would a transmission cooler inside the radiator. And we're exchanging the heat at that point from the oil to the coolant. So a couple of different ways that manufacturers have of getting rid of that heat. There are also, like for tow vehicles and things like that, aftermarket oil cooler kits available for some applications where I can install that. So say I have a truck and I do a lot of towing. I might be able to buy an adapter that goes between the oil filter and the engine, and it'll have the ability for me to connect hoses to it, and I can run those hoses up to an externally mounted oil cooler in front of my engine to try to get rid of some of that heat. So there is things available like that. that we don't see that for small cars or anything like that, but for trucks, things you're doing a lot of hauling or towing, that's something that you may find or will find for some applications. So that's lubrication. So feel a little bit better about how your oil is getting from your bottle that you pour into the engine to the different parts of the engine to make it last longer. And hopefully you see why it's so important to maintain the correct oil level and make sure our oil is of the correct type and clean.
Simple. It's just, like you mentioned, I think yesterday, is like a simple procedure as far as a maintenance thing that if you don't do can cause some big issues.
It is. It's the simplest thing. It is the most ignored thing because who wants to take the time to go get their oil changed when their car's running fine, right? So what do people do? They put it off and put it off. Or I don't want to spend the money on that this week. Somehow next week will be better. I don't want to spend it this week. And before you know it, it's been 6 months of next week. So this is probably one of the most neglected things on the vehicle, between having the wrong oil installed, whether it's done by a consumer or done by a shop the consumer is paying in good faith to take care of the car, or just ignored altogether, or allowed to run low on oil. You know, it used to be you checked your oil every time you got gas. Well, cars are so good now, people don't check their oil when they get gas. A lot of people never check their oil. They just think it should always be there, right? They take it in for service every 10,000 miles, whether it needs it or not. And magically, everything should just be fine. And the reality is it makes a big difference on how long a vehicle will last. And for some people, they don't care. They go buy a new car every 3 years. And they get rid of it at 60,000 miles. So they really don't care. That being said, I've seen engines blow up with under 60,000 miles because a customer bought a brand new car and never changed the oil. They took the salesperson literally when he said, "You don't need to do anything to this car." So they didn't. And at less than 60,000 miles, sometimes less than 50, the engine literally comes apart. And then the customer's mad because I always thought these were good cars. Well, they are good cars if you take care of them. So it really comes down to how long do you want your car to last? And for me, it's as long as possible. You know, I tend to buy things, I tend to buy what I want, and I tend to keep it for a very, very long time. Hence, I have a lot of stuff because I don't get rid of anything. Not that that's necessarily a good thing, it just is what it is. But I've had my pickup truck for over 32 years. I've had my pickup truck.
Dang, that's pretty awesome.
Yeah, I can
How
walk.
many-
What's that?
How many miles does it have?
It has, I think I got about 207,000 on it. I put a lot of miles on it for the first probably 15 years. And then in 98, it stopped being my daily driver. So the miles have clicked up a lot slower since then.
Yeah, it helps to have an understanding. That way, I liken the oil to the body, drinking water. I mean, it helps you to function, and you're hydrated and all that stuff, and then oil kind of is the same thing. If you don't put it in there, you dry up.
Oh, absolutely. And that's a great comparison because most people are dehydrated. Most people don't drink enough water.
That's true.
So
that is very true. I'm gonna go get water right now. I've been inspired.
Yeah, I drink a lot of water, and I do it intentionally. If I'm sitting down watching TV or I'm sitting down working, I drink tea in the morning, then I switch to water, and I drink a lot of water every day. And I make sure I do that because, like you said, Rebecca, it's lubrication. They always say, they say if you are thirsty, you're already dehydrated. So kind of going back to
Mhm.
our engine, if the oil light's on, you've already got a problem. All right, so let me stop this share. Come on, open up. Okay, so I'm going to share here. This is a training I went to by Permatex, and they were nice enough to share a PDF copy of their PowerPoints. This is not on Canvas. I should probably make a resource for this chapter and put it up in the information so you have it, because there's some good stuff in here. So this kind of talks about how to select and apply the right gasket maker. And I need to kick off a certain number of hours a year, and it's like, I'll take a look and see what's going on. It was a webinar, and I was able to get it recorded so I could watch it when I wanted. I like doing the webinars when they come with a free recording, so I don't have to necessarily do it at that day and time. And I was not expecting to learn anything. Or learn a couple of things. And I was impressed with how many things I did learn. And I thought they were worth some of them were worth sharing. So in this presentation, they talk about the types of gasket makers, gasket maker evolution. They got into some lab testing that kind of put me to sleep. Knowing your gasket makers, proper application and best practices, and then some technician resources. So I will work on getting this put up as a resource in the engines module. I'll make a page for it. So you do have access if you're interested. So types of gaskets, when we talk about sealing up an engine, we can use chemical adhesion, and this is by OEs. So about 30% of the things on the vehicle are just going to be a chemical adhesion. There is no paper gasket for from the factory. We are supposed to use a specific chemical sealant. About 30% is using just a gasket that's installed dry, is what we call it. So if I'm not putting anything on the gasket, we call that a dry gasket. And then usage percentage for cut plus chemicals, about 34%. So we do have things on the engine that we're using a combination of a chemical adhesion and a cut adhesion. And we can do that for a couple different reasons. Sometimes it is to keep a gasket from tearing as things expand and contract between like aluminum and cast iron. And since they'll expand and contract differently, in this case, the spray gasket sealant allows it to have some flexibility so it's not tearing apart the gasket, which allows the gasket to survive in that environment. Sometimes we have a gasket, but there are some corners or some places that the gasket's not going to seal well. So we're going to use some kind of chemical in addition to the gasket to seal up those specific parts of that sealing surface. Let's see, why are we, okay, I am. So Permatex products, it says here, used in 66% of the applications. That's a lot. Permatex is one of the big OE providers. So is Loctite. Those are the two manufacturers that provide a lot of stuff for the original equipment manufacturers. So it's not uncommon, whether I'm looking for an anaerobic sealant or a specific sealer, that they may actually reference a Permatex or Loctite number, part number, in the service manual. So RTV can be really broken into, or sealants can be broken into two main categories. One is a gasket maker, which is an extremely thick RTV silicone. So that is what's normally used in place of a paper gasket. Then there's gasket sealants, which are thin, non-setting, non-hardening, non-brittle sealants. So that's what I was talking about. It allows things to move. So they seal. I used to use a product called Hylamar on European stuff for head gaskets. And it was the same thing. It never sets up. It's sticky as all can be. And it seals, but allows the cast iron and the aluminum to expand and contract differently and do this little bit of slide on the head gasket on these big long 6-cylinders and not have the gasket fail. Because I'm not trying to glue the gasket in place necessarily, although there are some gasket sealants that are thin and do set up a little bit more, but they tend to be non-hardening and non-brittle. What we don't want to use is things that are not designed for the automotive industry. So some people use aircraft sealant. Oh, I love this stuff, and they paint everything with it. And there's some issues with that. First of all, aircraft don't use oxygen sensors. So one of our sensors that the computer relies on the most can be damaged by some of the chemicals we use. So we don't want to go, hey, this works great for roofing. I'm going to use this to put my valve covers in. And you may laugh, but I've actually walked into shops and they got the big tube of roofing silicone. They go, well, silicone. It's like, well, you're an idiot. I'm glad you're not working on my car. So we do want to use very, very specific materials. So gasket sealants can be used to make it cheaper gasket materials more robust, increasing adhesion, chemical and fluid resistance. So you heard me mention things like paper or cardboard gaskets. So I might want to make them a little more robust because fluids and things over time could really deteriorate those. If a flange is uneven, sealants help fill any gaps. So many times I may have slight imperfections, slight pitting, or something where I don't have quite that machine surface I did when it was new. And so sealants have a way of making up those little gaps so it doesn't give a pathway for whatever I'm trying to contain to escape. There are many types of gasket sealants available, just the same as gasket materials, each for different applications. If you're using a gasket sealant, you don't need a lot. A thin, even amount applied to the surface to fill any slight indents is all that's required. So one of the big mistakes people make is that, first of all, they use a lot of times they use RTV in place of a gasket sealant. And there are times you can get away with that, or it's your own choice. But the biggest mistake people make is when they use RTV, they use way too much of it. It is squirted out everywhere. And thinking, again, the thought process, well, if a little's good, more has to be like really good. And that is just not the case. Actually, it creates more problems. So pre-cut gaskets, the advantages of them are exact fit, no cleanup, OEM recommended and specified for certain applications, less time to install, easier to remove, no issues with sensors, difficult to keep in place sometimes, can be over torqued, causing them to split or tear, risk of getting bent or wrinkled, expensive, but billable as a physical part. So if I put a gasket on a customer's car, customer's going to pay for it. So one of the issues here, difficult to keep in place. This is why we normally would use a spray-on material or some kind of material on the gasket, is we're actually using that to hold the gasket in place for assembly. So yeah, we're making up any imperfections, we're doing things like that, but we're really holding in place. So one of the materials that we use for that is called high tack. And it is just a tacky material that sprays on, very similar to what you see here on this copper spray gasket, but it's high tack, and you spray it on, and it creates a sticky surface that allows a paper gasket or a gasket like that to stay in place. And we use that a lot for intake manifold, plenum assemblies, things like that. I got this big plenum and I got to line it up with these 6 little bolts or 4 little bolts, and everything's moving. And if I put a paper gasket there, it wants to move. I can bunch it up in the holes or I can tear it. So I really want to glue that gasket in place. Then when I set this on, it's not going to move. I can line up the bolt holes and attach it. So we use that quite a bit. that high tack. And I don't use it on everything, but that's normally what we use for that. The problem is other people will use something like an aircraft adhesive, which, boy, what a great adhesive. The problem is it's not necessarily O2 sensor safe. The bigger problem is, what about when we have to take this back apart? The high tack is going to allow me to take this back apart reasonably. The aircraft adhesive is not going to come apart reasonably. The gasket's going to tear off in lots of little pieces. I'm going to spend a half hour to 45 minutes cleaning the surface, being really upset at the last person. So that's another reason for using the correct materials. So chemical gaskets, multi-use, works in most applications, works better on imperfect surfaces. So for example, if I'm attaching tin to aluminum, either a gasket with some silicone, or the chemical gasket is going to seal that surface better because of that deflection, that movement. Or I need to go to a very soft gasket like a cork or something like that to make up for those imperfections, which is kind of interesting because I can buy really, really good metal reinforced silicone gaskets. They leak like a sieve because they're not good for that application. So even though they make a real expensive gasket for it, it actually works worse than the other ones. Better seal for chemical gaskets. The issue is the surface you're using has to be completely clean. So for example, if I'm trying to use silicone for a transmission gasket and I can't get the transmission to stop dripping, odds are I'm going to have a leak when I put it together, because when I put the silicone on with the pan, if there's any oil on there, that's going to keep the silicone from adhering to that surface, and now I have a leak. So they do make some special silicones that do a better job of that, but a regular silicone is going to have a huge leak. Always on hand, which is great, has a high success rate, less expensive than normal gaskets, long lasting. They say it lasts the life of the vehicle. It doesn't. It lasts a long time, don't get me wrong. But we do see silicone gaskets fail. We see them fail from the factory. But this is higher mile. For example, a timing cover gasket for Toyota, we do see them leak like on the 4-liter Tacomas, but a lot of times they got 150,000 miles on them, something like that. Messy to use, hard to remove and retire, requires time to cure. So the type of silicone you're buying can affect the cure time. So I can have a short cure time up to a 24-hour cure time before I can put the vehicle back in service. Another thing that greatly affects how long both chemical gaskets or pre-cut gaskets will last is your oil. As your oil breaks down, it becomes more acidic and it's going to attack these gaskets, just like your coolant, because we're going to get into cooling system tomorrow. If my coolant is allowed to break down and I don't change my coolant at the correct time, it's also going to become more acidic. It's going to break down these gaskets, whether it is a pre-cut gasket or a chemical gasket, causing a leak. So, another advantage to servicing your car regularly is statistically you're going to have less leaks. So, for example, my 2012 Camry with 198,000 miles on it doesn't leak any oil from anywhere. Part of that is engine design, a lot of aluminum, and transmission design, a lot of aluminum. But part of that is also that the fluids in both the engine and transmission have been serviced. And they're serviced at the correct interval. So I have all those additives that are so important to keep these seals and gaskets working are good. I'm not letting them break down. I'm not letting things become acidic and eat away at these gasket surfaces. So a little bit of gasket maker evolution, and this is for Permatex, obviously. There's other gasket makers out there. There's a European gasket maker, Durco, I've used a lot. I mean, there's other ones out there. But if we look here, 1936, boy, Forma gasket. Blue silicone, 1970s, and that worked great, except for it wasn't okay for oxygen sensors. You can still find blue silicone around. It's cheaper. It's okay for water passages or things like that. I've got a bunch of these because I don't use them. In the 80s, we came up with Ultra Black, and Ultra Black was really, and really today, been my standard up until I left industry. So Ultra Black's had a very, very long run, very good gasket. They came out with Ultra Gray in the 90s. And then they came out with this stuff called the Right Stuff 1 Minute Black in the 90s. And this was really designed for field service use. So the Right Stuff, and we have some of it at the school, is sticks to almost everything. And you don't want to be the person who has to be there next, because it is really difficult to clean up because it sticks to everything. Then they came up with the Optima series in 2017. And this is response to heat and newer technology. Right Stuff 90-minute black in a tube, 2019. And then 2020, you see we have a series. And if you notice, we have some different colors here. We have a gray, a red, and a black. So we have different colors, and those colors actually mean something. The early Ultras, do they show Ultra Black here? They also had Ultra Copper. Copper was the higher heat version. Red is higher heat. They also had a regular red silicone. So there's some other stuff you're seeing here that they left out of their history, but it kind of gives you an idea. The silicone has really evolved. Why would I go get the RTV blue that was invented in the 70s to work on my 2015 or 2006? That doesn't make sense. There's advances in technology. Again, going back to my TV example, you really don't want the 1971 Zenith in place of the flat screen. I'm just thinking that's probably not the best call. Oops. So OE trends, 4 important changes in the last decade that affect gasket makers. And this is why we see so many changes in silicone technology in the last 10 years. Aluminum is the most common metal being used. Challenge is soft metal can be easily damaged or create surface imperfections and expands at almost double the rate of steel. Turbos utilized on smaller displacement engines due to corporate average fuel economy standards. That's what CAFE is. CAFE is not where we're going to go get a latte. It's the corporate average fuel economy. Standards of lightweight vehicles. The challenge, turbos generate a lot more heat and put a lot more pressure on the crankshaft. Different types of coolants, as we'll see tomorrow. So the average car on the road when this was done was 11.9 years. With COVID, it's actually over 12 years now. A lot of them do not use green coolant. 2002 is the last year it was specified in the automobile. So we have a lot more coolant technology, a lot of different chemicals involved. And the more chemicals we use, the more possible chemical reactions we have. Oil specs, the friction modifiers. There are over 600 oil manufacturers, which means each company uses some proprietary aggressive additive package. So as we learned about oils, we learned about the different kind of modifiers they use, and our sealers have to be able to hold up to that. So in the lab, they kind of do some interesting tests. One is a dog bone tensile test. That's where they actually make dog bones out of silicone and pull them apart and see how many pounds it takes to pull them apart. There is the blowout test, and this is the in-house Permatex method. Ensures silicone resists pressure for a set amount of time. So they're putting pressure and looking for that silicone to push out and blow out. And then the shear tensile testing, silicone is applied to a combination of bare steel and aluminum to ensure bond strength, and gap spacers are applied for uniform sample thickness. And the samples are aged. 7-day aging is standard. Further aggressive aging in automotive solvents depending on formula, and high tensile strength. So they're looking for it to hold up to chemicals, be strong, not break, and not blow out to the side, not allow pressure to push it out of the way, and make sure it has good adhesion to whatever you're attaching it to. So you can see we've evolved a long way from simple aquarium sealant. So this talks about the ACE-TOX, I'm going to mispronounce it, ACE-TOXIMI or TOXI versus oxamine. Basically, it's the two different types of silicone. So the silicones release a fine powder-like substance during drying and curing process. This substance can coat the slots of the oxygen sensor, causing drivability problems with the vehicle. Products contain a strong odor and can be corrosive. So if you open up a tube of silicone and go, man, that really smells like silicone, don't use it on the car. The oxime-based silicones are made from low volatile components that cannot foul oxygen sensors. So they're going to have little or no smell when you open the cap, and they're non-corrosive. So that's a quick way. I don't care what it says. You open it up and boy, you could smell that silicone. Don't use it on the car. It's okay for coolant things traditionally, but I wouldn't even do that anymore, given all the different types of coolant and the different things that are going on. It's just not suitable for automotive use, even though it's still sold, even though I still get free tubes of it in different kits I buy and things like that. It's not, it's like they send me a tube with a gasket kit and the tube can't even be used with those gaskets. So I don't know if it's gasket manufacturers sometimes trying to throw something in because they're selling the gaskets. They didn't make the tube, they just bought the tube. We see this a lot with differential rebuild kits where we get a silicone that's not suitable for the engine use, but they're throwing it in the kit with the differential. But I wouldn't use it for a differential either because it's not great stuff for there. So the characteristics of our three different types of silicone. Black, this is where I need flexibility and oil resistance, and I'm probably going to be taking up a little bigger gap. So oil pans, timing covers, transmission pans, differential covers. So if I'm going to attach steel to aluminum, black is a great choice. If I'm going to attach aluminum, two machine surfaces, I'm going to want to use gray. So gray is a better for that. So valve cover, water pump, intake manifold, and thermostat housings if I'm not using a gasket. So I can use black a lot of these low torque places, such as a thermostat housing, some valve cover applications, but the gray is really designed to go where I have two machine surfaces that are going to go together and are going to be torqued. And the gray really resists being completely squeezed out and is going to give me a good seal there. That's what the gray is designed for. So a lot of manufacturers use gray for their factory timing covers on overhead cam engines. They use them for their oil pans when they have an aluminum oil pan going to an aluminum block, aluminum valve cover to an aluminum head. When I have machine surfaces going together, gray is the tube of choice. If I have surfaces where, and you can see I'm using a steel pan to a cast iron or aluminum block or cylinder head, now black is my better choice. Can I get away with black on a thermostat housing? Absolutely, I have for years. But also I usually will use the black in combination with the thermostat gasket. So I'm going to use a little bit of black to hold the gasket. A lot of times one side of the thermostat will have pitting on it. And so since there's pitting, I'll just put a real fine layer of the black, because the black is what? It's flexible, it resists oil and coolant. And then I'll put the gasket in. So I'm not really using the silicone to make a seal. I don't want something that's going to stay liquid all the time like I do with something to supplement the gasket. I actually kind of want to glue that in to cover those imperfections and create a good sealing surface. So I will do that with the black cap for years. The red or copper, it used to be copper, ultra copper. We're going to use that high heat areas, header, exhaust manifold, turbocharger, slip fit exhaust, things like that. It's designed around, high heat areas. And here they're using an example where they're using a 1 minute silicone on a header gasket or on a manifold gasket. I wouldn't do that. You're never going to get that together in a minute. So you need to give yourself enough working time. So it's a great picture, not what I'd ever do. Just like the example they're using here for the gray, this is a throttle body where you're going to be putting on a throttle body against it. There's a gasket that goes there. I'd never use silicone instead of a gasket there. That's something that comes on and off all the time. So Manufacturers almost always provide a gasket here. It's normally a paper gasket, or it could be a metal one. The metal ones are reusable. But I would not be, just siliconing that unless it was my last resort. I wouldn't do it to a customer as a part of normal service. So samples are pressed into a sheet, cut into dog bones, aged for 7 days, and they check the strength, the tensile strength. So you can see here, black has the lowest tensile strength because it's the most flexible. Here's the ultra black I've used for years. The Optima actually has less load. Right stuff is in the middle. Then you get into red, a little higher load, and then gray has the highest load, again, high torque. Here's the elongation, how much stretch does it has. Black has the most stretch. You can see the newer Optima and Right stuff have more stretch than the old Ultra does. Here the red, not as much stretch, and gray, least amount of stretch. That's why they use it for metal on metal, like cast aluminum machine surfaces. And here's an example of their dog bone. Here's their shear, where they're gluing two types of material together, or in this case, same aluminum to aluminum, aluminum to steel. How well does it hold it together? Here is their pressure, where they're actually putting this under pressure and looking for the silicone to squeeze out under pressure. So really kind of interesting how they rate silicones. Here they're looking at different products. So this is oil pan. Here's the original plastic oil pan used on the Ford diesels, 2011, 2012. This little quick plastic thing, it was just a quarter turn and came out to drain the oil. Didn't work so hot because it would come out on its own and you need an engine. So they've updated them to the metal pan they used on the later ones. And they're talking about, hey, where to use a black silicone. Here's an example where you use a black silicone. Here's some examples where they're talking the gray. Now, I found it interesting that they're recommending gray here on the V manifold, because we've always used black. And all the tubes for all the kits from Felpro and everyone else have always provided black silicone here, because you do have a fair amount of movement with this gasket. So I'm surprised that they're now calling for gray here. So that's something that's different than what we've done in the past. So when we get into some factory specifications, so the gray silicone, here's Honda specification, Chrysler, Mitsubishi, Suzuki, just some examples of where they're using the gray gaskets at the factory. Yeah. So here's the red. The red gasket makers are weathered and resist thermal cycling without hardening, shrinking, or cracking. So it is designed for high heat applications. And it sounds funny using this. I was really skeptical the first time I used ultra copper for this, but actually not using an exhaust manifold gasket on a lot of V engines and other engines where you have a cast iron manifold, you're better off machining the surface, not using a gasket, putting a light coat of silicone on it and bolting it up, and not having an exhaust leak. Many times on these vehicles, using the gasket, either you have an exhaust leak when you first assemble it, or the gasket burns out due to the imperfections, and then you're taking it back apart and doing it again, where the silicone does not do that. So this is something I've done for 25 years, since we first had a problem car and someone told me to use ultra copper on it. It's like, I don't know. I don't think it'll work, but we've already done this job 3 times. I've gotten pretty good at taking this off and put it back together. I can do it in about 10 minutes. So let's give it a whirl. And it works. So this is something that's kind of in my magic bag of tricks that I use. It's also great for in case there's any pitting or anything on the cylinder head surface where I can machine the manifold and get it smooth. I can't machine the surface. I might have some imperfections there on the head. So specialty gasket makers, they make some specialty gasket makers for differentials, some specialty gasket makers just for cooling systems. And that's because of the different kind of coolants we have. The OAT, HOAT, and IAT have evolved over the years. So now the technology of the silicone has also had to evolve. And so Permatex has a special silicone just for cooling systems. Sealant choices for rigid assemblies, anaerobic gasket makers and sealants are particularly good choice for sealing rigid machine surfaces with a maximum gap of less than 15 thousandths of an inch. I thought it was interesting that they're using it here for a water pump. That is not something we would normally use there in industry. I've never seen a manufacturer call for it. Normally there's gaskets there, or we're using a gray silicone. So it is interesting that they're calling for that now. Normally we only use this on case assemblies, things like that. But this is an anaerobic sealant. I have some in my toolbox. A tube like this will last you 20 years normally, and it doesn't harden. So the one I've had in my toolbox, I've probably had 20 years. You just don't use anaerobic sealants very often. You see the example here is older Volkswagen and Porsche air-cooled engines, motorcycles, small engine applications where we're putting together assemblies that are machined is normally where we use that anaerobic. We don't normally use it on water pumps. So it's interesting they're now moving in that direction. A proper application, best practices, how to replace. So here, inspect for cracks. When they're talking about gasket removal, they're pushing using a spray gasket removal that chemically removes the gasket. The reason is that if you use razor blades or other surfaces incorrectly, you can create weak points, or you can prevent gouges in the surface that you've cleaned, allowing pass for the gasket to fail. And then it talks about you selecting the appropriate gasket maker based on temperature and performance. They talk about anti-seize. So anti-seize prior to assembly prevent seizing, gulling, or corrosion in a high temperature area. So many times we use anti-seize on exhaust components, specifically things like sensors, O2 sensor threads, things like that. You can use them on exhaust bolts, although normally not used. It certainly can be, but we definitely use it on any kind of sensors or anything else we put in with exhaust, or things we assemble, turbo lines, things like that. They're going to be subject to high heat and high heat cycling. We're going to use an anti-seize. You see where here we're applying the gasket depending on the application. Most of the time it's about 1/8 of an inch around is all you need. 1/4 inch around is huge amount of gasket material. And if I'm doing a 1/4 inch, I'm not going to make it round. I'm going to actually not use the adapter, hold it flat, and just kind of do this with the surface. So it spreads out and it's really thin, but it's wide. I don't want a 1/4 inch round bead laying around something like we're seeing on the manifold here. If I'm doing a valve cover or I'm doing a metal oil pan, then I would want that bigger 1/4 inch round with the black. I'd want that more material. So then when I put it up, it's going to take up those imperfections. It's going to seal correctly. So the more machine the surface, the less silicone we're going to use, the smaller the bead. And then assembly and torque. Assemble, then immediately hand tighten the bolts, allow the gasket to sit 1 hour. Before going to final torque. Well, the reality is that's not practical. I can't do something, wait an hour and come back. So generally we need to find gasket materials that allow us to quickly assemble, or understand that my torque is going to be sufficient because I've used such a small amount of silicone on the surface, and I'm going to continue assembling, but I'm not going to be pouring liquids in it for a period of time. When using RTV gasket, proper reassembly requires the following: apply a continuous bead of silicone to the mating surface, assemble parts with the bolts finger tight to ensure contact is established while the silicone is still wet, let it sit for 1 hour, then torque all fasteners to proper values, and then after 24-hour cure time, fill the necessary fluids and return the vehicle to the customer. So we can see there's several issues here. One, you don't have an hour between every step. And especially there are things where I have stuff I have to attach some of the bolts, that I have to stack something else on top that I'm siliconing that has bolts to go through the first thing, and then I have to torque everything together, and I have to do that in a pretty short amount of time. That there isn't that hour. So this is where you see the difference between what a manufacturer is recommending and what you can actually do. Can you imagine, hey, we're going to do an oil pan on your car, but you can't pick it up till tomorrow afternoon. Why? I thought it was only a 2-hour job. Yeah, but we got to let the silicone sit for 24 hours before we put oil back in. Is that practical? No, of course it's not. So they do make chemicals that allow you to bend these rules or break these rules. And that's why it's important to use the right chemical. But I did find it interesting going through that the times they're looking at are completely unrealistic. No one's going to go back and retorque things. A lot of stuff you can't get to after you put other things on. Imagine, gee, I'm going to do a valve job on your car, but I need a month because I can only work on it one piece a day because I need to keep going back and retorque it and doing this. It's just not practical. So here's the different silicones that Permatex does. So you can see fastest drying time, shorter drying time, ultra black, 8 hour for full cure. That's not your, runtime. If you notice here, the right stuff, 1 minute, 1 minute return to service time. So it's not fully cured, but that's your return to service. I've used a lot of Ultra products over the years. I've never had a problem with returning them to service in a reasonable amount of time. If I'm doing something like a timing cover or something like that, I normally will use the gray and I'll give it an overnight setup. So I might put the engine together tonight. I don't put oil in until tomorrow morning and run it because I want that overnight cure time. Honda recommends a 24-hour cure time from the factory on their gray silicone. So that long cure time is very consistent. So you kind of got to keep in mind what you're doing. How much labor did you go to put this together? How big a job is it? And those kind of things. Something like a thermostat housing, I'm going to seal that sucker up, put it back together, fill it up, and that sucker is going to be on the road in 30 minutes. It's just a non-issue. Return the vehicle back to service 1 minute. They're promoting their right stuff 1 minute. Maximum Performance talks about the Optima series a little bit. And gasket summary. So it talks about some different gaskets, cork and paper, RTV silicones, metal gaskets, and closely machined surfaces with a minimum gap of 50 thousandths, where we're using anaerobic sealant. So you can see we rarely use that. This has a couple of different training portholes. So there is some Permatex training and there is some pro tips on the video in their YouTube channel. So again, I will get this up there and this is all free. And that's it.